Welcome back to Physics 141 Online. The last topic from Chapter 7 deals with another way for us to understand the motion of a particle in terms of the potential energy that it experiences. And so this gets at the relationship between the conservative force and the potential energy function associated with that force. Let's consider a path for an object that moves along the x direction. And so as it moves along the x direction from a position x1 to x2, its potential energy changes. And we want to look at how we represent that using the definition of potential energy change. And here we remember that we defined this as, in a way, that it was minus the work done by the conservative force. The work done by the conservative force is the integral f sub x dx. So minus that integral gives us the potential energy change. And all that this reminds us in the first integral sign is that a change in potential energy as the object moves from point 1 to point 2 is made up of many tiny changes in potential energy as it moves through all the intermediate spots. So from x1 to x2 it passes through x values, and as it's doing that its potential energy is changing by small amounts every time it increases its x value just a little bit. So when we compare this integral on the left with the integral on the right, where I've brought the minus sign now into the integral sign, we can see that the quantity f sub x dx, the force times a small change in x, is equal to the change, the tiny change in the potential energy function for the object that moves through a distance dx. And that may not be especially clear if you're not familiar with calculus, but just by inspection of those two integrals we can make that identification. And so when we rearrange this and solve for the f sub x term, we see a new relationship between the force and the potential energy function that we define based on that force. The original definition told us how to calculate the potential energy change if we know the force. This now turns it around and says if we know the potential energy function, then what can we do with that? We can calculate the force. And we do that by taking the derivative or finding the slope of the potential energy curve. And the minus sign is just there because of the way that the potential energy change is defined. So this gives us some significant qualitative insight into the behavior of an object. Let's just use as an example the familiar potential energy function for a spring. We have shown that knowing that the force was equal to minus kx, we calculated the potential energy function as 1/2 kx squared. And so that's a familiar parabola if we plot the potential energy versus x. Remember, of course, that as you compress the spring, that gives negative values of x. If you stretch it, it gives positive values, but the potential energy function is completely symmetrical. It doesn't matter whether x is positive or negative. So with that potential energy function, if we take the derivative or the slope of that function, using the rule for doing that, the 2 would come down in front, multiply the 1/2 to give a 1, and then we would have k times x to the first power. And the minus sign in front of it, if we carry that along, gives us minus kx. And so this is consistent with what we used in order to calculate this potential energy function. So this just shows if we start with the potential energy function 1/2 kx squared, we get back the force law that's known as Hooke's law, and we know that has to be true. So that's how this formula works, is it allows us to find the force if we know the potential energy function. Now qualitatively, let's look at the behavior of this object. Let's imagine that it starts off at x equals 0, which for a spring would be when the spring is neither stretched nor compressed. And at x equals 0, the slope of this curve is 0, right? It's flat. So the slope is 0, which means the force is 0. And that's what we mean by an equilibrium point. An equilibrium point is a point where an object is where it feels 0 net force. So at the origin, at x equals 0, at the bottom of the potential energy curve, the object would have no force. If we imagine now compressing the spring a little bit so that the x value becomes negative, let's use this formula here qualitatively to see what happens. The slope of the potential energy curve at this point is negative because it's decreasing. So minus a negative value is a positive value. And that means that at this point, the force is positive. So if the object is pushed a little bit in the negative x direction, it feels a force coming back toward the origin. And that makes sense. We know that that's the way springs behave. When you compress them, they push back. So for x less than 0, f sub x is greater than 0. And we can do the same thing for positive values of x. This is now when you stretch the spring. We know that springs pull back. And look at this point. At a positive value of x, the slope of the potential energy graph is positive, so the force is negative. So as you stretch the spring, it pulls back in the opposite direction, which means for positive x, the force is negative. And that is the characteristic of a stable equilibrium point. What we mean by a stable equilibrium point is at the bottom of the curve here, at x equals 0, it's equilibrium, the force is 0. If we push it a little bit to the left, then a force is exerted, bringing it back toward the origin. If we pull it a little bit to the right, a force is exerted in the negative direction that propels it back toward the origin. So a small displacement causes it to return to equilibrium, and that's a characteristic of a stable equilibrium point. However, there are other kinds of equilibrium points on potential energy diagrams. And so let's take a look at this one. We're not going to worry about where this curve comes from, but let's just imagine that we know that there's an object that can move along the x direction, and it moves in such a way that it obeys this potential energy function. It's influenced by a force that has this as the potential energy function. And these points, A, B, C, D, E, and F, we can think a little bit about special points here, remembering, of course, that the force is minus the derivative or minus the slope of the curve at each point. So the simplest one is, of course, at point D, which is down in the bottom of the potential energy curve. Once again, the slope there is 0, so it's equilibrium. And if you push it to the right, the force is in the negative direction. If you move it to the left, the force is in the positive direction, which makes D a stable equilibrium point. But now let's look at B. What about point B? This is interesting because, of course, the slope is 0, which means it's a stable, which means it's an equilibrium point. But imagine now moving it a little bit to the right. So if it moves in a positive x direction from point B, the slope is negative, which means the force is positive. So if we push it to the right from point B, the force is in the positive direction, which makes it want to keep going. So the same way it works if we move it a little bit in the negative direction from point B. The slope is positive, which makes the force negative. So if we push it to the left, the force keeps on going, makes it keep on going to the left. And that makes point B an unstable equilibrium point. If you could keep it right at point B and balance it there, it would stay there. It would feel no net force. But if you just give it a little push one way or the other, it'll run away. And that's called an unstable equilibrium point. That might be like a ball on top of a hill or a roller coaster at the very top of a high track. You might be able to balance it and keep it right there, but if you push it a little bit one way or the other, it's going to fall off the hill and go moving in one direction or the other. And there's one more point that we'll mention here, and that's called a neutral equilibrium point. At point F, assuming that this potential energy curve flattens out, when it gets to this plateau at point F, the force, of course, is 0. And if we move it a little bit to the left or to the right, as long as it doesn't go too far to the left, then there's still no net force on it. And so the object doesn't return from where it came, but it still stays in equilibrium. So point F is not really that special of a point. It's just a place where there's no net force, and if we move it, it still doesn't experience a net force. These other points, A, C, and E, although they might look like they have special significance, really don't in terms of the potential energy diagram. So this potential energy diagram understanding gives us a way of qualitatively analyzing the motion of an object, the behavior of an object, if we know its potential energy curve, especially if it's not such a simple one like this. I'll do an example in class where we're given a potential energy curve and we do something a little more quantitative to analyze its motion and the location of these special kinds of points. I'll see you in class.